To experiment 2. In this session, we're going to be looking at intermolecular forces and also buffering. Now, you might say, what in the world do those two really have in common? Why are we putting those two together? The commonality is that both of these subjects are important to biology because much of biology takes place in water-based systems. And so because of that, we need to really think about the forces that occur between biological molecules, and that would be largely intermolecular forces. But they also, since they're occurring in the water-based systems, the cytosol, that type of thing, those systems are often buffered, or normally buffered under most conditions. So we need to think about that. So the commonality is that intermolecular forces and buffering both take place in aqueous systems, where much of biology takes place. Now, it's true that sometimes there are reactions and other things that take place inside of membranes. Think about the mitochondria or the cell plasma membrane. There are things that happen there, and those are not water-based, and those are still important. But nonetheless, much of what we study in biochemistry and biology is in the cytosol and other places. So we're going to take a look at those today. So really the goals of the experiment are, number one, to look at organic and intermolecular forces, to investigate some physical properties related to those, particularly organic compounds, and to connect the intermolecular forces to physical properties. Right, so bringing those two together. That's really going to be part one of the experiment. Part two is really going to be looking at a sample buffer calculation, making a buffer, preparing it, and then also demonstrating the power and the properties of a particular buffer, and also a molecule. Really, we'll look at a molecule glycine that has buffering properties. All right, so let's think about our intermolecular forces. And again, these things are present largely in organic compounds, which is mostly what biological molecules are. They're mostly organic. There are some metals that occur in there, iron and a few other things, but it's largely organic compounds. So remember, there are London forces, dipole-dipole forces, and hydrogen bonds. Those are the three type of intermolecular forces that we see most commonly. So remember, London forces. Remember, these are temporary. It's key to circle this here. Temporary dipoles between molecules, resulting in a cohesive force. All right, so nonpolar compounds such as pentane, methane, many of these others. These are the only type of intermolecular forces that occur between those two. However, what we should know is that all compounds, regardless of whether they're polar or nonpolar, can exhibit London dispersion forces. All right, these are again temporary dipoles between molecules. And this figure helps to highlight that. And again, here what we'll find is that each one of these circles here and here, largely represent an atom, or it could be a molecule, it could be anything. And all of these atoms and molecules have, of course, electrons that are here and shown here. What happens just under really quick time periods, 10 to the minus 15 seconds, is that electrons will arrange themselves, and a whole bunch of them, like a whole bunch of electrons, just might end up on this side of the molecule over here, creating a partial negative charge. So it's not a true negative charge like we might think about in general chemistry, but it's a partial negative charge that's there. Well, as a result, since this has a partial negative charge, that impacts the compound that's here. And this one will rearrange its electrons to be attracted to this, and so as a result, it does have this partial negative here, but notice it creates, by doing so, a partial positive. And we would also see that partial positive here. As a result, these are attracted to one another. Right? So these are London forces, and they're cohesive, that is, they are bonding. Right? And so largely when we talk about intermolecular forces, we think about those that are attracted. It is possible, for instance, if we had this guy and had a negative charge and something else came in negative here, just say a negatively charged chlorine or something, that there would be repulsion. And that does happen, but we like to think about the really attractive forces. All right, so number one is London forces. Number two are dipole-dipole forces. These are the most common type. And again, noticing that whereas we had a temporary dipole before, this one is a permanent dipole built into the molecule. All right, and so again, these are attractive forces. Here we see acetone, our fingernail polish remover type of compound. And remember that this one's important because it has this dipole. It's not really a good arrow. I get a proper arrow. All right, so this, as remember, shows the dipole moment, going from the carbon into the oxygen, and as a result, that's a permanent dipole. It results because of a difference in electronegativity. Oxygen is much more electronegative than carbon, and so again, we end up with a partial negative here and a partial positive, and because this continually occurs, lots of acetone molecules could be attracted to one another, sort of lining up. All right, and this would be, again, because of a permanent dipole, and this is an attractive force. Because it's permanent, it actually is stronger, and it's more likely to happen. Remember, the London forces is just a really quick temporary dipole that sort of comes and goes under really quick time scales, and they result. Now, this is a very similar molecule, just sort of showing, highlighting the red part here, which is more negative, and the blue parts, which are more positive. Of course, it does have a double bond. We'll draw it in, but the point is not really to show the double bond, but to show the fact that it's a permanent dipole. And so then we could find that there would be other molecules, for instance, that would line up here, and they would be attracted, and again, because there would be this partial positive and a partial negative here, and these would be these permanent dipoles, which allow the attraction. And so because, of course, biological compounds have lots of carbon and oxygen and nitrogen, these can create these dipole-dipole interactions, which are cohesive and they're also attractive. Third type is a special type of dipole-dipole, and this is known as the hydrogen bond. It's sort of the strongest of the strong intermolecular forces. And again, this results because we have an association of this hydrogen on one atom, right? So this hydrogen right here, and some electrons on this nearby atom. Now remember, this isn't just any hydrogen, it has to be a couple of things. That this hydrogen needs to be connected to an oxygen as it is here. This could also be a nitrogen or a fluorine. Of course, here it's clearly oxygen, but that creates a dipole. And then these four parallel lines, and usually we use 3 or 4 parallel lines to show its attractiveness to another oxygen. And so again, this needs to be an oxygen, has a lone pair of electrons, and it could also be a nitrogen or fluorine if it had those pair of electrons. But again, here it's just an oxygen. And again, there's this attractive force, which we call a hydrogen bond. And this is probably one of the more well-known intermolecular forces. And if we talk about it in DNA, all of the bases are sort of attracted to one another because of intermolecular forces. Proteins, there's lots of hydrogen bonding going on, and so we can see those attractions. But nonetheless, those are the 3 types of intermolecular forces: London forces, dipole-dipole forces, and also hydrogen bonding. And we're going to look at these in our experiment today to see how these impact physical properties. All right, so in this first part, we're going to take a look at 2 molecules, water and glycerin. Again, noticing that water has an OH group here, and so does glycerin. It has 3 of them. All right, so it has lots of hydrogen bonding possibility, and we're going to take a look to see how these are important, particularly in terms of their ability to flow. Right, so how do they adhere to one another? Individual water molecules, individual glycerin molecules. All right, and so have these water and glycerin as they flow. All right, so do they? And if they're more attractive, what we're going to find out likely is that if they're more attractive, they're not going to flow nearly as well. All right, and so that's one part. So it's really in part 1. And so as we do this, you want to do a couple of things. You want to observe the flow of 2 substances and correlate those to the molecular features. All right, so this is what we're going to do in this protocol 1. We're going to compare the flow of 2 substances. We're going to place a drop of water and a drop of glycerin on separate watch glasses. We're going to tilt them up, and we're going to see how far they flow. And so when we're doing this, I want you to think about what are the properties of water and glycerin, and then what it really happens. What observations can you make when we lift up this watch glass and watch them flow? So let's take a look at viscosity. And we're going to look at the 2 molecules that we've seen on the screen. That would be glycerin and water, both hydrogen bond containing molecules, and how viscous they are. All right, and so we'll do that. We're going to, very simply, we're going to put a drop of each one of them on a watch glass, and we're just going to see how well they resist flow, because viscosity is really resistance to flow. That is, molecules want to stay the same, stay together if they are really viscous. All right, so let's put a drop of glycine right there. I'm sorry, let's drop of glycerin. We'll use glycine later, and a drop of water. All right, so first of all, I'll test the glycerin. All right, so I move this up, and so notice we do have our liquid bead there, and it's moving down. All right, so you might make some observations as we're doing this. You want to write down how fast the glycerin is moving. All right, so it's, again, moving from the center out towards the edge, so it's just moving down vertically. All right, so that's a good bit for glycerin. Let's do the same thing for water. All right, so we can see that water, in a really quick time, moved to the edge of the watch glass, and there it dropped off. Right? And so we held it probably for just a fraction of the time that we did for glycerin. So the goal of this part was just to get us to think about viscosity. Think about how substances, how they resist flow. And again, we want to correlate this to the intermolecular forces. So again, we know that water and glycerin both have hydrogen bonds, but they had fairly different viscosities of flow. Right? So again, might just for display, obviously, glycerin's flow is really slow. Water flowed relatively quickly. And so we might want to think about what the difference is because they both have hydrogen bonds. Now we're going to use this idea of viscosity that we talked about here in this section in the next part to look at this a little bit more quantitatively. As you've thought about the data, one of the things that we want you to do is in this part one, we want to answer these two questions in your report. What kind of forces are present in pure glycerin and pure water that hold these molecules together in a liquid state? We've already sort of hinted at that. And then the viscosity really is a measure of a substance resistance to flow. How much it resists the flow. So something that's really viscous, think like molasses, doesn't want to flow. All right, so which one of these substances then had a higher viscosity? In part two, what we want to do is take this a little bit further and really sort of put some data, some numerical values to this part two and think about how they flow, one molecule compared to the other, and we're going to vary some of the intermolecular forces. And so really what this is that we're going to look at the viscosity of compounds, and we're going to measure it, and particularly as these substances flow down a capillary tube. There's a really narrow tube, and so we're going to use glass pipettes to show this, and so we're going to get some small capillary tubes, and we're going to measure several substances with different intermolecular forces and see how they flow. And again, remembering that viscosity is resistance to flow. So something that's more viscous, like molasses, or something else along those lines is not going to flow nearly as well as something that does not have strong intermolecular forces. Now we're going to look at viscosity, and we're going to try to put some numbers to it and actually get some quantitative data to our qualitative data we saw in that first section. All right, so what we're going to do is we're going to use flow through a capillary tube with small tubes. So we're going to use this pipette with this narrow part as our flow. And we're going to watch as a couple of liquids go from this mark to this mark, which is 4 centimeters apart. I've already marked it, and 4 centimeters, and we're going to calculate, we're going to measure the time that it takes for it to flow 4 centimeters. So we're going to do this for a couple of different compounds. So first, let me show you how I did this part. So again, I put a marker on this capillary tube, this pipette, but think about it as a capillary tube, 4 centimeters apart, and I've done that several times. And we're going to look at three different compounds: pentane, pentanone, and pentanol. All right, so remember, pentane is just straight carbons and hydrogens, and so it has London forces. This pentanone is kind of like acetone; it has that permanent dipole, so it has dipole forces. And then alcohol has the OH group, and so of course they have hydrogen bonds. So what I'm going to do is we're going to look at each one of these, and I'm going to withdraw solution up into this tube, and then we're going to make the time that it takes for each solution to go from the one mark, the top mark, to the bottom mark. Right, so I'm going to use my thumb just to make sure we get it right to the top mark, and we're going to let it drain out. And so I'm going to say start and stop for the timing. So let me get this back up. All right, so this first one, pentane. All right, so it's at the starting mark, so I'm going to say start, stop. All right, that was our first one. We're going to repeat it 3 times to make sure that we're getting accurate measurements. And once again, we're at our top mark, so I'm going to say start and stop. It's down to that second mark. So pentane is, gotta get it to the top. Right, we're now at the starting point, so start and stop. All right, so we're going to start and stop. All right, so that's thinking about pentane, which has only London forces. All right, so let's do the same thing now for pentanone. Okay, remember pentanone, the difference is it's still 5 carbons, but it has dipole forces because of that ketone group. And I'll get this one. All right, so it's now at the top, I'm sorry. So I'm going to say start, stop. So you might have noticed that one was a little bit slower. It took a little bit more time. So I'll get the second one. So I've got it in position. So now I'm going to say start, stop. And I'm going to do it a third time. So I've got it in position. So I'll say start, stop. All right, so pentanone, again, you can just sort of notice that it was a little bit slower in this particular case compared to pentane. So in this section, next part, we're going to actually look at pentanol, and particularly you should notice the structures on all of these. We've been showing them on the bottles, so make sure you're recording those to make the correlation. But this one's 2-pentanol. Again, noticing that the OH group is coming off of the second carbon, and just to back up again, notice this was 3-pentanone. The ketone's on that third carbon, the middle one, and then pentane's just straight carbon chain. So let's see if we can get some values now for pentanol. So I'll get the pentanol in position. So now I have it ready, so I'll say start. Stop. All right, so once again, sort of qualitatively, just looking at it, you know that pentanone is a little bit slower. All right, so I have it now in position, so I'll say start. Stop. And we get one more. So I have the third one now in position, so I'll say start. And stop. All right, so we've seen now the comparison of pentane, pentanone, and pentanol. Commonalities, they all have 5 carbons, they're all pentane groups. Pentane would just have London forces. Pentanone would have primarily dipole forces, although because it has 3 carbons and hydrogens, it would also experience some London forces. And then pentanol has the OH group, so it has hydrogen bonding, and also it has some London forces because of all the carbons and hydrogens that are beside that OH group. And then you might even say you can have some dipole forces because of the carbon-oxygen bond. Right? So those all together would then impact the results here for this flow. And we'll talk about calculating those results in just a second. So we looked at pentane, pentanone, and pentanol, those compounds, to help us look at the difference between London dipole forces and hydrogen bonds. We're going to do 3 more, and we want to focus in on London forces. London forces are often thought to be the weak, and they have this temporary dipole, and maybe they don't impact flow nearly as much. But we want to take a look at that and see really how important these how important the London forces are. So for this part, we're going to work with 3 compounds. One of them is heptane. Remember that heptane is 7 carbons, so it's just 7 carbons in a row. Then we'll also look at decane. You might remember that decane is 10 carbons in a row. So again, just 10 carbons connected together with some hydrogens. And then a compound you likely haven't heard of before is hexadecane. And hexadecane is 16 carbons, right? So long chain. So again, noticing the structural formulas that are on there. So again, we'll go ahead and work with these. We'll do 3 trials on each one of these. To see, so we'll start with heptane, and we'll pull up heptane into here, and I'll get it into position. Just it's now in position, so I'll say start, stop. Try this one again. We'll get the second one into position. It's now in position, so I'll say start, stop. So this third one, I'll get it into position. It's now in position, so I'll say start, stop. And let's do one more for that one. This one, I'll get it into position. This one's now in position, so I'll say start, stop. All right, that was for our heptane compound, which again is 7 carbons in a row. Okay, so we have 7 carbons in a row. Let's try 10. Make sure so 10 carbons, which would be decane. So it's in position, so I'll say start, stop for that one. So this one's in position, so I'll say start, stop. So this one's in position, so start, and stop. All right, so we've done heptane and decane, so we'll do one final one, and this one is our hexadecane, so 16 carbons in a row with the appropriate number of hydrogens. These are all saturated compounds. All right, so if you've been paying attention then with the heptane and the decane, you might make an educated guess about how this one is going to go. So you might make some observations. So this one is in position, so start, stop. So this one is now in position, so I'll say start. And stop.
You're right. He's right. He's right.
So this one's in position, so start. And stop. Okay, so in this one we've seen a little bit of the impact of London forces. So going from a chain of just 7 carbons into a chain of 10 carbons and 16. Again, remembering that they're carbons plus they're saturated with hydrogen, so it has to include that. But in terms of the length, that's important. So we have to think about the importance of London forces. So bigger compounds, longer chains, would have more surface area and hence more ability to have London forces to interact. One other aspect, they might also have a little bit of tendency to tangle up, right? And so getting tangled up, and so kind of like a bunch of cords, being charged, people charging their phones all at the same outlet, right? Those cords get tangled. In the same way, we can see something like that with really longer compounds. But ultimately, we see the primary effect is on the London forces. All right, so we're going to continue to think about London forces and dipole-dipole forces and hydrogen bonds in the next segment of our experiment. All right, so we just got our data. We looked at pentane, pentanone, pentanol, and then we did heptane, decane, and hexadecane. All right, so we got those values. We want to get some viscosity values for this, some actual rate flow values. So that can help. Those numbers can sometimes really help us see and understand a little bit more about viscosity. Saw back with water and glycerin, it was just a very obvious tip of our watch glass. However, in this case, what we can do is put some numbers to it. So let's try that. So we want to take a sample calculation. Let's say we just had a substance that took 1.4 seconds to go those 4 centimeters. Remember that, those 4 centimeters that was on our little tube. And so what that would look like is we could get a flow. It's kind of like miles per hour. Is that we could actually have centimeters per second. And so we would go 4.0 centimeters per 1.4 seconds. And that would end up giving us our flow, kind of like miles per hour, centimeters per second. And if we did that math, we end up getting 2.9 centimeters per second. And that would be our flow. All right, so our flow rate. And I guess we can do seconds here. All right, so that would be a sample. Let's go ahead and do that then for our pentane, pentanone, and pentanol compounds. So we'll do that here on this page. And so pentane, that's pentane. And for pentane, we ended up having 3 values. And those 3 values were 1.63 and 1.75 and 1.55. Right, those are our values. Again, they're not exactly the same, but they're fairly close. Now, what we can do is get an average of those, and that's really how we get errors out of data. Is we take several values and we average them. We can add 1.63 plus 1.75 plus 1.55 and divide by 3, and that gives us our average. And if we do that, then as you might expect, we get 1.64 as our average. All right, so these 3 right here, those 3 compounds then, or those 3 numbers are 3 values for pentane. We have some, as we know, for other ones. All right, so these, we'll just make sure these are individual rates. All right, so sorry, individual times. These are, of course, in seconds, and then our average is in seconds as well. Now, we have one more thing we want to get, and that's the flow that we just talked about. So we're going to take our 4 centimeters, we're going to divide it by 1.64 to get those centimeters per second flow. And if we do that, then when we talk about flow, how fast it flows, and in terms of that rate, and that again will relate to our viscosity, but that would end up being 2.43 centimeters per second. That would be our average rate of flow. Now, we can do that. We've seen it for pentane. We can do it for pentanone. It's the one that we know actually has intermolecular forces of dipole-dipole. This one was a little bit faster in terms of flow. I'm sorry, a little bit slower. It took more time. So again, these are our 3 values. And then we can actually put those together, average those out, take these 3, add them together, divide by 3, and then we'll get our average here time. And then that corresponds to flow, how fast this went in terms of our flow, centimeters per second, 1.74. And then finally, we can get to our pentanol, which we indicated had the hydrogen bonds, right? So the hydrogen bonds are the strongest. So as a result, what we see here is that because intermolecular forces were stronger, when pentanol, it took a longer time to go that same 4 centimeter distance. So this one, 7.49, 7.47, and then also 7.85. And again, noticing that these numbers aren't all exactly the same, but they're in the same ballpark, pretty close, which again is why we average the data. And again, we get an average of 6.0, and then that maps to a flow rate of 0.526. Again, that's centimeters per second. All right, so again, we notice this trend that, again, the one with London forces, they had the highest flow rate, and the dipole-dipole, the slower one, and then pentanol had even the slowest. And that's what you might expect, right? Because then you have stronger molecular forces with pentanol, and even pentanone compared to pentane. They hold together more strongly and it resists the flow. And that's really what viscosity is. It's resistance to flow. And we can see that in these values here. And again, these values are just indicating not negative values, but again, just indicating these three compounds. Those were the three that we did. Now, we did three more, and remember these next ones were all very similar in the sense they all had London forces, but we want to see the impact of London forces on the molecular weight, that is the length of the chain. Right, so we look at heptane, decane, and then also hexadecane. Right, and hexadecane, recall, was the one that was 16 carbons long, decane's 10, heptane is 7. So let's go ahead and look at the values then for heptane. Make sure to record those. 1.81 for the first one for heptane, 1.96 was the second one, and then 1.71. And once again, these are the individual values, individual measurements that we took. And then for decane, similar in terms of, it was slower, but similar in terms of the rates. We're in exactly this, the times weren't exactly the same, but again, we can average these out to get a better rate. Right? So these are individual values. I'll let you notice that seconds. And then hexadecane was the slowest of all, 9.63, 11.54, so there's some variability there for sure, and then 10.49. And again, these are all the individual times. What I want you to do, now that we've done one for you, is to, first of all, calculate the average. Make sure we put this in your report, calculate the average flow for those three, and then also calculate the flow in terms of centimeters per second. Right? So again, this average should be units per second, we're just averaging those. And this is flow, right? So you want to do that. So your job is to fill in this spot and this spot for those compounds, so you get to practice at calculating the rate, the average speed, and then also the flow rate for those. All right? And so do that and put those in your report. In part 3, we're going to investigate how intermolecular forces, how that impacts vapor pressure. Right? And so really, what is vapor pressure? Well, in an enclosed container, some of the molecules, and we'll just draw this down here. So if we have a beaker-like substance, or a beaker-like container with a lid on it, and down here at the bottom we got some liquid, what's going to happen is that with vapor pressure, some of these liquid molecules are going to escape, and there'll be gas molecules. Let's just use a G for gas. And the gas molecules will be in what we call the vapor phase, gas molecules at room temperature, sort of normal temperature. And so those molecules that have higher vapor pressure, that is, have higher intermolecular forces, are able to overcome those intermolecular forces and get into the gaseous phase. So in this particular part of the experiment, we're going to get you to think about how the intermolecular forces, how it really relates to vapor pressure. All right? So do higher intermolecular forces, does it increase the vapor pressure? Does it decrease? All right, so recall that vapor pressure is the ability of a molecule to escape from the liquid phase and go into the vapor phase. And so again, it has vapor pressure because, again, vapor molecules are gaseous molecules and they exert pressure. We're going to look at the vapor pressure of two compounds, water and pentane. So we've seen those both already today, so we're going to look at them and compare their vapor pressures. All right, so we're going to do this by putting 2 drops of pentane on a watch glass. We're also going to put 2 drops of water on a watch glass. And we're going to think about how their intermolecular forces, pentane only has London forces, water has hydrogen bonds, how that impacts then their vapor pressure. All right, so the more molecules get into the vapor phase quicker, higher vapor pressure. If it takes longer, then that molecule would have a lower vapor pressure. So we'll do this with pentane and just a little flask of water. And so we'll make sure we suck up a little bit of the pentane and start a timer in just a second. So put 2 drops of pentane right there, splatter just a little bit, and we started our timer. We'll do the same thing with water. All right, and so what you can notice again is that water has a nice big blob. And you can see the pentane is already starting to go, and just a little bit of it left. All right, and so I think we can safely say that all the pentane has evaporated at this particular point. All right, so certainly less than a minute for that pentane to evaporate. Now notice with the water. The water still has a pretty large amount of it there. I would think it'd be safe to say that at least 98% of the water is still there. Hasn't really looked like it's changed much at all. Okay, so we're back, and the pentane only took about 33 seconds, and we're now at about 56 minutes, and the water is still there, just barely, I think. And I think there's just a couple little droplets there. All right, so we'll call it, say, 56.5 minutes that it took for the same amount of water to evaporate. Now again, we need to connect this with the intermolecular forces. So think about pentane, 33 seconds or so, it took it to all evaporate, whereas water took it about 56 minutes. And again, it'll vary depending on the temperature in the room and airflow and that type of thing. But again, there's a significant difference, and we can connect that directly to the intermolecular forces. All right, so you might just think about the London forces in pentane, how strong they are compared to the hydrogen bonding in water. And we sort of know this intuitively, or we've heard it in class, the difference in strengths. But really, this is a great way to illustrate it, right? So we're talking a few seconds, 33 seconds, all the way up to 56 minutes. All right, so that helps us understand, with some of the other things that we've done today, how intermolecular forces really can impact things like solubility, vapor pressure, flow that we see with organic molecules, and those are the primary ones that make up biological molecules. Now we've gathered some data in this part 3 of your experiment. We want you to answer a couple of things. The pressure increase that occurs through the evaporation of a liquid is called vapor pressure. And based on your observations in part 1, again, going all the way back to part 1, so go back there, would you predict water or glycerin to have a higher vapor pressure? All right, so we gathered some data in this part 3, and this question wants you to go back to part 1 and revisit that and think about that data now based on vapor pressure. All right, and which of the substances, water or vapor, has stronger intermolecular forces based on your viscosity measurements? Again, we didn't exactly work with water and glycerin in this part 3, but based on what we gathered in part 3, let's bring that together with part 1 to help us understand that. And then finally, this third part, we want you to rank the following 7 compounds from lowest to highest vapor pressure based on what we know about the intermolecular forces. All right, so these forces right here, or these compounds right here that are illustrated, all right, we want you to rank those, again, from lowest to highest vapor pressure, all right, based on what we know about the intermolecular forces. All right, in this next part of the experiment, again, we're changing gears just a little bit, and we're going to look at buffer, all right, and buffering. Now again, the connection to that last part was intermolecular forces are the things that occur between water and a substance that's dissolved. There's 2 other substances that are dissolved in water, so they're all in this aqueous solution. One of the things that's important in just about every biological solution, whether it's in a cytosol or maybe in an organelle, is that the pH is kept appropriately. Physiological pH, we generally say is 7.4, and that's what we, in humans, we often have. However, there's some organelles like the lysosome, which is down about pH of 5, and they're maintained at those particular pHs by buffers. That is a chemical system that helps to maintain the pH, because we know that pH is important for the physiological properties of these biomolecules. All right, so let's look at a sample buffer calculation. We're going to take a couple of slides to work through how we would actually prepare a buffer, and then we're going to make a buffer. So here's our problem. We actually want to prepare 250 milliliters of a 0.5 molar phosphoric acid buffer. And that buffer system, we want to maintain it at a pH of 7, and we want to use sodium phosphate monobasic and sodium phosphate dibasic. All right? And so we need to do some calculations. So first we need to find the molecular weights of these guys, and so we find the monobasic is 119, this guy, the dibasic is 142, and we can see here the chemical formulas of these guys right here, the dibasic and the monobasic. Monobasic here, and dibasic here. And so we have those, and again, the pKa for these is 7.2, so we're going to make a buffer near its pKa, so we're making a buffer pH of 7, and this is 7.2. All right, so this is going to be our buffering system, and this is the reaction. And again, remember, this is an equilibrium reaction. Le-Chatelier's principle is involved here that this can change if we add more H+, it'll shift back that direction. If there's OH- that's added here, it can react with the H+, and again, buffers, it helps to maintain the pH. And really, remember, that's the goal of a buffer, is to maintain the pH. So how do we do this calculation? Well, we use the Henderson-Hasselbalch equation, which is this one right here. We've seen this before. Again, the pH of a solution is related to the pK of the buffering system, and theoretically, and then the actual compositions of the conjugate base, HA, over its acid. In this particular case, what we want to do is we want to have a pH of 7. That's our given. That's what we want to attain. And the pK of the phosphate buffering system is 7.2. All right, so those are two of the values we know. And we're trying to figure out really what are A and HA. That's really our goal of this part of it. To say, all right, we want to make a pH 7 buffer, pKa 7.2. What ratio of conjugate base and acid do we actually need? Well, let's go through the calculation. Using the Henderson-Hasselbalch, classic for this, that we have this set up. And again, we want to solve really for HA on the bottom, A on top. And so to do that, what we can do is subtract over the 7.2. So we subtract 7.2 from this side and minus 7.2 from this side. Recall, we can do that mathematically because we haven't changed anything, because we're doing the same thing to both sides of an equal sign. And we end up getting this negative 0.2 is equal to the log of A minus over HA. So if we want to get rid of this log, right? So we need to get rid of these logarithms to get to just A over HA. And if we take the anti-log, right? So remember log and anti-log. So if we take the anti-log of this, 10 to the x of log, that cancels this one out. And then what we'll be doing is really taking the anti-log, or 10 to the x of this minus 0.2. We show that here. So the anti-log of 0.2, the anti-log of log, these will cancel one another out. And that leaves us, if we take the anti-log of minus 0.2, 0.631, and then we have A over HA. And again, we're left with that because the anti-log crosses out that log. So now we don't exactly know the individual concentrations of these two, but at least we know a relationship. And really we can think about this as 0.631 over 1. That is 0.63, some ratio over ratio 0.631 of A minus over every one of HA. So we can almost write the HA in brackets here on the bottom, right? And so we have this ratio. We'll see that next on the next slide, where again we can write that ratio here, and then we can move down here and you see where I put the 1. So I've got the 0.63 over 1, that's the ratio. So for every 0.631 of this, we have one of these guys. Right, so we're getting closer, right? Not exactly to what the individual concentrations or amounts are, but we're getting closer, and we know a relationship. And so what we can do to figure this out is that we can actually multiply both sides by HA. Why would we do that? Well, if we did that, we could actually cancel out HA on this side, as we've done. And we would get HA over here on this side, and again, the 1 goes away, and so we would end up with 0.631 HA is equal to, there's an understood 1 right there, 1 A minus. And as a result, we know a relationship between HA and A. And we can use that next to calculate the sodium phosphate buffer concentration. And again, because we said at the beginning that we need 0.5 molar, we would know that all of that molar solution needs to be composed of HA plus any A minus. We don't know right now what HA and A minus are. However, we did figure out just the last slide that 0.631 HA is equal to one of these guys. So if we plug this in, this relationship in for A, right? So this is really equal. So this 0.631 comes in, and so now we have this 0.5 equal to HA plus 0.631 HA. And we add those two together because again they have the commonalities HA. We end up with this. So we know 0.5 molar is equal to 1.63 because we add this understood 1 here plus 0.63, and we get 1.63 times HA. And again, we often just call it HA, but we'll put brackets here just to make sure that we know that that's concentration. And so we know that the concentration of HA should be 0.307 molar. We can also then figure out, this is the exciting part about A minus, because we know it's 0.193 because we can just take 0.5, subtract what we know from HA, and we end up with this value, and that's our concentration of A minus. The point is, if we create a solution that contains this ratio of compounds, we should get to a solution that has a pH of 7.0. All right, so let's look at the final step. So we know the concentrations, now we need to think about the masses that we have for these compounds, for each one of these, and so that we can mix them together to make a buffer. All right, so we figured out the concentrations on the last slide of this HA, and then it's A minus, so this would be the A minus sodium phosphate dibasic, as we saw. And again, since we know that it's 250 milliliters or 0.25 liters, we take the concentration. Remember, molarity is moles per liter. So if we take 0.25, this moles per liter times 0.25, the liters cancel out, and we're left with the moles of the sodium monobasic. Same thing for the dibasic. We end up with 0.048 moles of this, the dibasic. And then finally, for each one of these, we can actually then get the number of grams. So that would end up being 9.21 grams of this monobasic, and also 6.86 grams of the dibasic. And if we measure these out on a balance, and then add those to a 250 milliliter flask, add water, and we can test for the pH. It should be really close to 7. And then once it's at 7, if it's not quite there, we can add some acid or base, as is typical, to get it to a pH of 7. So now that we've calculated how to make a buffer and gotten the appropriate amounts of sodium phosphate monobasic and sodium phosphate dibasic, we're going to go ahead and prepare that. All right, so we said 250 milliliters, so we have a 250 milliliter volumetric flask here, and we're going to put our solids in there. And to do that, we're going to use a powder funnel. This is very helpful to help get these salts in there without spilling too much of them. So we're going to try to just gently put some in, hopefully not spilling on the table. All right, so that's the sodium phosphate monobasic. Here's the dibasic. So we're going to put that in, and again, we use the same powder funnel just because they're all going into the same vessel. All right, so that's our dibasic. I need to just get it to go in just a little bit more. There we go. And of course, one of the things we want to do is go ahead and add some distilled water to the funnel. Any solid that's in there, that'll allow us to get it down into here. Right? And so then also we can pull this out, maybe, and then add a little bit to the neck of the funnel. What we want to do now is, now that we've gotten the solid in there, we want to fill this up part of the way. We're going to use a pH probe, and we want to leave a little bit of room because the pH usually isn't the exact number. In this case, it's going to be 7. So what we want to do then is we want to make sure that we leave a little room to adjust it with acid or base to the correct and desired pH. We should be close, but sometimes they can be off. So we're going to add a little bit of water. And then we're also going to add a stir bar. So a stir bar, and a stir bar, we'll add that, and that'll allow us to help to mix it. So we're going to put it on a stir plate, and you can see it's already started to stir. And again, the idea is that there's a magnet in the plate that's spinning, and then there's also this magnetic stir bar. And we're going to turn this up and let this dissolve. While that's starting to dissolve, I'll show you what we're going to do with the pH probe. All right, so I think that was going a little too fast, and the magnet got off kilter. But we're going to use our pH probe. Adjusted it. And again, this is a pencil thin one, so it fits down into the neck of it, but it only goes so far. Notice it doesn't quite now hit the top of the liquid. So we're going to add just a little bit more liquid, and again, we always want to leave room so that we can add acid or base if we need to. It's not exactly pH of 7, and it'll almost surely not be pH of 7. Also, adding the water here will give us a little bit more water volume and make it a little bit easier for some of these salts, the sodium phosphate, dibasic, and monobasic, to dissolve. And so they're actually dissolving fairly well. So we're going to allow those to dissolve. Maybe while they're dissolving, we'll check to make sure we get enough room for a pH probe. And again, notice I haven't put quite enough in, so we need to be able to, I should point out the little white part that's here. That's really a key part of the probe, and that needs to be underneath the water level. So we'll continue to add a little bit more water. All right, that's probably about right. As we can turn the spin down just a little bit to see that, hey, we just about right. Enough water into the probe, but we still need to allow some of this solids to dissolve. One of the things is we get a sort of a sneak peek at the pH of this buffer. Again, as these continue to dissolve, it's about 6.6. So notice that's a little short of 7, where we want to be. However, we still have some solids that need to dissolve, and those could actually alter the pH a little bit. So we're going to let this rotate. Okay, so we're getting to the end. I think all the solids have dissolved, and as you can see, as those dissolve, we actually got the pH up close to 7, so 6.97. It raised up just a bit, and that's actually pretty good for pH 7 buffer. We can add a little bit of HCl if we wanted to adjust the pH. So we'll leave it there, pretty happy. But that's sometimes over titrate. And so we're good there. One of the other things we'll need to do, think about it, is we'll stop. And so we have this magnetic stir in the bottom. That actually takes up volume. And so because of that, we want to remove the magnetic stir from this. Without getting, so we actually use the stir bar extractor. So it's a magnet inside of a plastic rod there. And that will actually allow us to pull out the stir bar. And then we can actually add some water in to a fill line that's actually in the there's one class, and there's a little line there, and when you get to that line, it's exactly 250 milliliters, and then we can also just test that we're about pH of 7, right? And so again, 6.97 or so, that's really good. So remember, this is a buffer, and a buffer really helps to maintain the pH for that. So one of the things we can do is actually just we can test the pH to see if really it's doing its job. And so we'll compare that to say water. And so let's go ahead and put in about 100 milliliters. I think we'll go with about 120 or so. This phosphate buffer, and then we're going to add some strong HCl to this. We'll just put it to the side. You can see there again, we're still maintaining that about 6.96 or so pH, and we'll add some HCl to that. Tip this off. Add some HCl to the solution, and we'll stir it up just a little bit. And you'll notice, of course, adding acid to a buffer should lower the pH, and it goes down just a little bit, right? From 6.97 to about 6.94, and really it's going back up to 6.5 or so, it's bouncing around. And so there's not been much change in the pH that's been maintained, which is one of the goals of a buffer, is to help maintain the pH. Now let's compare that to approximately the same volume of water. You have about 120 milliliters of water. We'll make sure that in between, using our pH probe, we clean that off. And we'll add our pH probe to water. And again, noticing water, it's a little bit higher, but still sort of in that pH 7 range. It's about 7.8, so it's higher than our buffer, per se. Let's add a little bit of HCl to it and see how it changes. Notice that there's a significant difference, right? So we went from about 7.8 with the same volume of HCl down to 2.45. So there's a drastic change in the pH. That would not be good for a biological system. If the pH changed that much, it can actually change the structure and change some other things about that. So which is why the importance really of buffers. We saw our phosphate buffer really maintain the pH drop just a couple of points, but we saw that the pH in water went down to about 2.4, so it's a really big drop. So showing the importance of buffers in a biological system. Next, we'll talk a little bit about glycine, a natural buffer in the body. Now, sodium phosphate, dibasic, monobasic are in solution, in natural solutions in our blood, for instance. However, there are other molecules such as amino acid glycine. And these also act as buffers because they have these ionizable groups. This O comes off to free an O minus, and we have this NH3 here. And so what we find out is that something like glycine with two ionizable groups has two pKa values. And we call it pK1, pK2, because they're both pKa values, but we want to differentiate because one molecule has two of these. And so based on what we've seen so far is that we can figure out that glycine would act as a good buffer right around pH of 2.35, and also then again at about 9.6. At other places, it might not be such a great buffer because, again, there wouldn't be this organization of acid and conjugate base. But at those particular values, they would act as a really good buffer. And we're going to take a look at this to see how glycine can be a good buffer. So we've made a phosphate buffer, and the phosphate buffer is something we typically would make in the lab to actually buffer the pH. We know that it's important for biological systems, but we know that biological molecules, such as amino acids and sugars and other types of compounds, can actually have pKa values, and they can actually buffer on their own. So let's take a look at one amino acid, glycine. And glycine actually has two pKa values, one down at about 2.35, as we put in our beaker, and also one at 9.6. One dealing with more of the carboxylic acid, and the other one dealing with more of the amine group. Right? So we made a solution of glycine, and then adjusted the pH to be down around those pKa values. And again, this will help demonstrate its ability to act as a buffer. All right, so again, pH of 2.35, again, we're at about 2.4 or so. And so now what we can do is actually think about our last part where we saw water and phosphate and how those differ in their ability to maintain the pH. Water's pH drastically went down to 2 or so with a little bit of HCl, and phosphate nearly stayed the same. So we're going to add, again, about 50 microliters of base to our pH 2.38 glycine solution. So we're going to put that in and we're going to mix it. And so again, we're adding a little bit of base. And notice, as we would expect, the pH starts to go up just a little bit. Went from 2.38 to 2.39, so not much. Again, showing the ability of it to act as a buffer. And I'll just add another alkali in to help demonstrate this. And so stir it up, and again, goes up to briefly to 2.41, 2.4. It is going in the correct direction. That is going up, is what we expect. But again, it's resisting the pH, which is really the goal a buffer is to resist the pH. And so again, we've gone up to about 2.4. And that's, again, one of its pKa values at 2.35. And it'll basically buffer within about 1 pH unit of its pKa. So 2.35 will go from about 1 to 2.35 to 3.35. And in fact, whenever we eat a buffer that's really in that lower pH range, which is not often, glycine is a common example. All right, so here's its other pK value from the amine group, about 9.6 is that pK value, and we got our solution at about 9.73. And in this case, what we can do is we'll actually add a little bit of acid, because we're going the opposite direction, and to see that we can actually add acid as well, help to maintain this, since we put this in here and stir it around. And again, it does start to go down just briefly, as we would expect for an acid. Let's add a little bit more. And again, it goes down to about 9.68, but then pops back up again. Some of that dropping quickly moving up is just diffusion of some of these, and then we'll add another value. All right, and so again, notice this one does drop it a little bit more, and we're down to about 9.68, 9.69. So it's really helping, the glycine is really helping to maintain the pH at that 9.6. Now, I wouldn't do it for every pH, but it does it right around 2.35 and around 9.60 would be the example. And I can actually add some more base here just to show that, how much does it go up? And again, it resists pH both ways, and so again, notice it goes from 9.68 to 9.69. But this is the importance of buffers, for one, but then also how biological molecules themselves can act as buffers, and they can actually help to maintain the pH of a solution. All right, so in this summary, a couple of things that we've looked at. We really had two major parts of this experiment. One of them I'll just label IMF, and for intermolecular forces. And so we thought about, generally, we reviewed the general information for intermolecular forces. That is that we have London forces, and we have dipole-dipole forces and hydrogen bonds. And again, the London force is the weakest, dipole-dipole in the middle, and hydrogen bonds are a special subset of dipole, and so they're the strongest. We related those intermolecular forces to both viscosity, all right, and vapor pressure. All right, and we've seen how intermolecular forces can impact both of those. And then finally, on the second half, different part of this, we looked at buffers. We looked at a sample calculation for a buffer. We actually prepared the buffer, right? So by measuring out the sodium phosphate dibasic and the sodium phosphate monobasic, and then we thought about this and said, all right, glycine, it can act as a buffer, and it can actually resist additions of H plus and OH minus, and so we'll be able to look at that. All right.